Okay, so here's another thing that I would very much like you to be aware of. It's part of who we are as part of this large universe. So here's a question. You're allegedly paying attention to this video, to this lecture. You're probably not dancing around, so you're probably not moving, you're probably sitting somewhere comfortably, I hope. And so the question is, are you really, really sitting still? Okay, so we're going to talk about what the earth is doing while you might be sleeping or just sitting still. Maybe your mind is wandering around, so you feel like you're moving, but hey, how about the physical movement that actually happens while you are sitting still? You're going to learn that you're not sitting still. Things are moving with you, and things are moving in several ways because Earth is moving in several ways, and things that Earth belongs to move in several ways at surprisingly fast speeds. All right, so here is the first two types of motion we are going to talk about. The Earth is moving, first of all, around its axis of rotation. You probably know the Earth is rotating around its axis that goes south to North Pole, right? And it does that in how long? You probably recognize the fact that the complete rotation around its axis, spin around its axis, happens once every day. So it takes 24 hours. Another thing that I want to point out for you here is that, hey, look at these speeds. So if you're living close to the equator, you're moving with the surface of the Earth. It's really 1670 kilometers per hour, very close. If you can convert that into miles per hour, if you really want to. So it's still, a large number. If you live, which is very likely, somewhere in the northern hemisphere or just, somewhere in the southern hemisphere, but at a parallel, that would correspond to, say, Shenandoah Valley. So that would be this situation. You're still moving very, very fast. And it actually turns out that these speeds are much faster than the commercial jet travel, which is why the jets cannot keep up with the sun when going opposite Earth's rotation. All right, so that's pretty fast. Of course, it's close to zero actually if you live very close to the pole, right? That's zero. Interesting, isn't it? Okay, so now, fine, the Earth rotates around its own axis, but at the same time, here's the second type of motion we're going to talk about. The Earth itself with its own axis, which is always going to point out in the north direction, okay? Which actually the north can be found by the star Polaris. We're going to talk about that in chapter 2. Right, so the Earth rotates around the star in the center of our solar system, and that is the sun. So Earth orbits the sun or revolves, and it takes 365 days in average. We call that a year. That's why actually we have that measure of a year. It's because of this type of motion, and that's why we have the day, because of that type of motion. All right, so Earth is here. In average, this is the distance, 1 AU or 1 astronomical unit. All right. Which is about 150 million kilometers. You're gonna deal with that in some of the homework problems on mastering astronomy. All right, so there is a plane associated with this motion. We are going to mention that again in the next chapter, I think. So yeah, how fast this motion happens? Well, we can calculate that. You can take the whole circumference of this orbit. You can calculate it once you have the radius, right? And you get that circumference, divide by the time, which is 365 days, and you get the speed, an average speed of 107,000 kilometers per hour, right? So this is how fast you, on the surface of the Earth, is orbiting or revolving around our sun. Amazing, isn't it? And the motion doesn't stop here, all right? There is the third type of motion. It turns out that the sun is moving randomly relative to the nearby stars, the other nearby, right? Because we talk about the local solar neighborhood. So that is, shown here by kind of a cube of matter inside the galaxy. So we're here somewhere in one of the spiral arms of the Milky Way, right? And there are lots of stars around us. This is the sun, and these are other stars. And you see they're all moving in different directions, and those directions are illustrated here by little arrows. Okay, so look at the typical relative speeds of all these stars relative to us, the sun, that is, or relative to some other stars. Huge, 70,000 kilometers per second. All right. Okay. It turns out that the stars are just so far away that we cannot easily notice their motion. Actually, they do seem to be located at the same place every time we look at them, year after year after year. It's very, very little, because they're so far, very little change in where they are in our sky, because they're just so far away. All right. So, yes, we, as the sun or the solar system, we're moving relatively random relative to the stars that are our neighbors, but then all this local group of stars are revolving around the center of the galaxy. So this is the galactic center, and we are moving, you see that, right? We're revolving around the center of the galaxy. So think about, here's another analogy that you might want to consider. So there is a stream of water, and it's moving this way, okay? And maybe you noticed, maybe you did a beautiful hike lately, and there are some groups of leaves. If you look closely, there are leaves that are moving in different directions, kind of randomly, right, inside that group. So leaves move randomly inside that group of leaves, and yet the whole group is going down the stream. So that's pretty much what our stars, our solar neighborhood, and our own star, the sun, is doing, right? So you can imagine again this whole solar neighborhood, right? And they are they're moving, right? The whole thing is moving around the center of the galaxy. How fast? Again, pretty fast given all those distances. So look at that radius, 28,000 light years. We just learned about the light year, right? So circumference, that is 2 pi times radius. Okay, so you can calculate that, and this is the radius. And you calculate that, and then you divide by the time. Okay, this is 200 and 30 million years, right? Time for a complete revolution around the galactic center. And yeah, you're gonna get some crazy numbers about that, just how fast this kind of cube or group of stars are moving around the center of the galaxy. All right, well, guess what? We're gonna keep moving, right? So far, what did we see? That hey, the Earth itself, right? Remember, is rotating around its axis. The Sun is somewhere in the middle, and the Earth is moving around, right? These are some other planets. You can actually see this beautiful diagram in your textbook, and you can zoom in. It's a really made at really high resolution, so you can actually read all the labels. I think this is Neptune, right? This is one of the dwarf planets. It's Eris, I think. Pluto might be here, right? So another one of the dwarf galaxies, dwarf planets around the Sun. So anyway, yeah, so this is the solar system, so we're moving, right? That's first type of motion, second type of motion. The third one, we're moving in the solar neighborhood, right? So somewhere here's the Sun, and then we have all kinds of stars, and it's a beautiful diagram because it shows actually some properties of the stars around us. I think this is Aldebaran, red giant. We're going to talk about those things in the next chapters. And so you put, all this group of galaxies that is here, and it's rotating around the galactic center. Okay, the thing is, the galaxy itself, this Milky Way, beautiful galaxy of ours, right, exists, you probably remember, we talked about that, in the local galactic groups. So this is Andromeda, or M31. It's another name that galaxy is known for, and there are, I think these are the large and the small Magellanic Clouds, some of the dwarf galaxies, right? But the thing is, they are moving, especially Andromeda and Milky Way, they're moving towards one another. You probably heard that in about 5 billion years they're actually going to collide with one another. So the thing is, right, there are all kinds of movements here. So yeah, they move towards one another. Now this is this one, right? It's one of the small groups in the Virgo supercluster. This is the Virgo cluster. And again, they're moving actually away from one another. And this whole thing is in this diagram, just this little thing, and so on, right? And you get all these local superclusters. And actually, the Virgo cluster is just a tiny dot in the observable universe. And there is a lot of motion of the galaxies around one another. Remember, here in the local group and within the supercluster, and definitely now all these things are moving kind of away from one another. At least that's what we measure. So actually, here's an analogy that I want to present to you that we should try to help explain this motion of the galaxies away from one another. So first of all, here's the concept we want to discuss. Galaxies are carried along with the expansion of the universe. Well, what is that we measured? How is it that Hubble actually was doing Hubble had figured that out at the beginning? Okay, he figured what happens with galaxies, how they move, and it was observed that. But here's an analogy. It's called the raisin cake analogy, right? So say you have I'm gonna need a little space here to make a little table. So we're gonna do it here. So we have resin, I'm gonna use another color, resin 1, okay, then we have resin 2, and then we have resin 3, and so we have now distance from us, that is the local resin, okay. All right, so before baking, okay, so that is before baking the cake. As you can see here, right, they're all 1 centimeter apart. So away from the local resin, resin number 1 is 1 centimeter away, the resin number 2 is going to be 2 centimeters away, and the third is going to be 3 centimeters away. Well, how about the same distance but after baking? Can you tell? In 1 hour, that was the duration of the baking, the raisins were displaced, right? So now the first raisin is actually 3 centimeters away from the local raisin. The second raisin is 3 plus 3 is 6 centimeters away, and the third is going to be 9 centimeter. All right, so basically what I want you to see is that resin number 1 traveled, so we have distance traveled, it's going to be 2 centimeters, right? Because it used to be at 1, now it's 3 centimeters. How about resin number 2? It's going to be 4 centimeters, the distance that traveled in 1 hour, and resin number 3 traveled 6 centimeters, and they all did that in 1 hour. So you can actually look at the speeds, right? So again, so we have resin number 1, resin number 2, and resin number 3, okay? And we have their speeds. Speed is distance traveled over time. We have distances here. So the first resin traveled 2 centimeters per hour. Resin number 2, 4 centimeters per hour. And resin number 3, 6 centimeters per hour. So, what can you tell? Can you say this is going faster? Right, so the resin that was further away, right, the more distant one, it looks like it's traveling faster and it's racing away faster than resin number 2, right? So it's still racing away, moving away, but slower. Nice, right? Yeah, so this is what Hubble measured, that all galaxies outside the local group are actually moving away from us, and then by measuring their speeds, we realized that the more distant a galaxy is, anything that we measure in the distant universe, the faster they are. And so, yeah, the conclusion is that we actually live in an expanding universe. I hope this raising cake analogy and all this discussion helped you figure out what's happening here. So if you were to meet a question like this in your homework already or in the exam by the end of the week, which says, what does it mean to say that the universe is expanding, right? And you're going to read the possible answers like, oh, the galaxies are getting further apart from each other. Yeah, we just discussed about that. Another possibility written here is that each galaxy is getting larger. No, we didn't mention that, right? So this expansion doesn't happen inside any galaxy, or also the solar system is getting larger. No, we did not see that happening, right? So that expansion of the universe happens just in between actually clusters of galaxies. So the correct answer would be definitely not, would be A, not, definitely not all of the above. So let's summarize. Our Earth looks like it's behaving like a spaceship, right? We're never sitting still. Even when we feel like we're sitting still, we are not, right? Because we're on the surface of the Earth and the Earth rotates on its axis, and it does that with fairly large speeds, okay? More than thousands of kilometers per second, especially in the places on the surface of the Earth where most of the people live, right? I mean, if you really insist on living at the poles, any one of those, you're not going to move that fast. But even if you don't do that, you're still moving at hundreds of thousands of kilometers per second around the sun, right? So remember, the average radius of this orbit is 1 astronomical unit, or a few billion millions of kilometers, right? Forgot the exact number. It's definitely, you can find it. It's in these lectures, in the math skills, I think. So yeah, there are quite a few ways. And so if that, just as if that kind of motion was not enough, remember this tiny thing, the sun, with all these orbits of Venus, Mars, Mercury, and then all the other planets, all those, they are just a dot in this solar neighborhood, right? And all these solar systems, basically, some of these stars might have planets, some don't around them. They're moving really fast around one another. And all that solar neighborhood is one dot here in one spiral arm of this galaxy, and they're moving away. Look at these numbers, right? Rotate around the Milky Way's center. And the Milky Way itself, right? So all that thing, it's either this or the other. I forgot. One of them is Andromeda, right? But this is the local group, and the galaxies, look at these arrows, right? They move around one another. Again, Milky Way and Andromeda, they're moving towards one another. That's what we're able to measure so far. And they're eventually going to collide, as many other galaxies actually do out there, in millions or billions of years. All right, that local group, again, that's just one speck of this huge universe of kind of a web of galaxies, filaments of clusters of galaxies, and that keeps expanding. All the clusters of galaxies are moving away from one another. So yeah, this is what we measured so far. This is what we know about how we're actually moving every single second, right? And you can tell fraction of a second, given all these huge numbers, these huge speeds at which all these motions